All right. It is the 11th of September. Amen. May God have mercy on their souls. Amen. Father, Son, Holy Spirit. Amen. And it is 12:29 p.m. And we are going to continue discussing the exercises from Dummett and Foot. Let's see about this. Okay, so all right. Let's see about this. So, exercise 17 has us looking at this. Let me get to it. Exercise 17, show that if n is greater than or equal to 4, then the number this looks a lot like the previous one, right? So let me take a look at the previous one again. Yes, okay. The number of permutations in S sub n, which are the product of two disjoint cycles two cycles. Isn't that a trick? No, but is n times open parentheses n minus 1, close parentheses, open parentheses, n minus 2, close parentheses, open parentheses, n minus 3, close parentheses, all over 8. So, right, so this is kind of like the last proof, right? Well, think of building such a permutation step by step. First, you need to pick 4 distinct symbols that will be moved around, right? So next, you must break those 4 symbols into 2 pairs, since each transposition swaps exactly 2. Finally, you note that the order doesn't matter, right? So swapping A, B, then, so swapping open curly bracket A, comma, B, then close curly bracket, then open curly bracket C, comma, D, close curly bracket, is the same as swapping open curly bracket C, comma, D, close curly bracket, then open curly bracket A, comma, B, close curly bracket. So it's you're swapping these pairs, right? So I'm just going to say colloquially, without going into the exact notation, swapping AB then CD is the same as swapping CD then AB. And inside each pair, the order doesn't matter either. So the problem boils down to, okay, how many ways are there to choose 4 symbols and split them into 2 unlabeled pairs? That's why the count turns to how would I say this? Like n combination 4, I think that is, times 3. I believe that's right. Equivalently, you get this. These things are equal. This looks like some sort of chemical thing. I've always thought it looked like a chemical thing, but maybe yours came first. Maybe the combinations and combinatoric came first. Let me think. No, I don't have a good enough knowledge of the history of chemistry to really decide on that. So to really think about that in any way that is, to some extent, right? It's like formalization of mathematics happened, then it's like, well, physics happened, then chemistry, and it's like, well, but that specific symbology, what is it? No, symbol type thing, it's not, I don't know the specifics on that. That's what I'll say for now. But anyways, let's go on to the proof. So one method you can use for this is you can say, okay, sequential choice right? So let's choose the first 2 cycle. Open parentheses n, and then 2, and that is top to bottom, times 3, or equivalently, no, okay. I don't have to write words for that, like I did in the, so this is equal to n times, open parentheses, n minus 1, close parentheses, over 2, options. Come on. Options. Oh my gosh, how in the world? Okay, so, jeez. Options. Now, choose the second. Disjoint 2 cycle from the remaining n minus 2 symbols. So we've got open parentheses n minus 2 over 2, so n minus 2 combined with 2 in combination with 2, which is equal to open parentheses n minus 2, close parentheses, open parentheses, n minus 3, close parentheses, over 2 options, right? So it's interesting. Sometimes I think about this sort of idea that probability theory should be considered one of the foundations of mathematics, and I don't necessarily buy that for now, but I don't know. My mind could change on that fairly easily if I was shown certain things. Like if it was like, okay, it exists in the foundations, but it's like it's not as foundational, let's say, as something like it's not topology. As something as a like set theory. You know, it's like, well, that's pretty foundational, man. I don't think probability theory and set theory are on the same level, but it's whatever. Well, no, it's not whatever. It matters, but but anyway, since open parentheses a b, close parentheses, open parentheses c d, close parentheses is equal to open parentheses c d, close parentheses, open parentheses a b. 1 second, did I do that? Yeah, change the order. Each permutation has been counted twice. Divide by 2. What does this get you? Well, let me take a look at the camera and see. Yeah, camera's still going fine. Previous video, we'll see about it, but the rotation got switched, so I don't know if I put it in the editor and I click rotation, if I put it on YouTube, that it's going to be fine and dandy. So you're hearing it here first if you see this. So anyway, 5 by 2, what does that get you? rhyme in half the time. So, okay. So the total count, come on, what the heck, man? The total count, I'm just gonna finish this part and then I'll get a new marker, is in combination with 2, so open parentheses n over 2, close parentheses, and then open parentheses n minus 2 in combination with 2, so open parentheses n minus 2 over 2, close parentheses, and all of that over 2 is equal to open parentheses, no, is equal to n times open parentheses n minus 1, close parentheses, over 2, that times open parentheses n minus 2, close parentheses, open parentheses, n minus 3, close parentheses, over 2. All of this, that whole product right there, that goes over 2. I know, it's pretty cool. But, so that is equal to n times open parentheses, n minus 1, close parentheses, open parentheses, n minus 2, close parentheses, open parentheses, n minus 3, close parentheses, all of that over 8. You can get all of that over 8, right? So that's method 1. That's method 1, I like that. But there's another way which is a lot easier. Like this one I like because it's like, it happens in steps. Like it's very rational. Like it doesn't require too much brute force memorization. You can kind of derive it if you want, but it doesn't mean that it's easier because, well, sometimes seeing multiple steps is a lot harder than seeing just one big step, even if that one big step requires a lot more memory. So method 2, which is this direct grouping method. So choose 4 symbols. From n, n in combination with 4 ways, right? So partition them into 2 unordered pairs. Three ways. So the total is n combination 4 times 3 is equal to n times open parentheses n minus 1, close parentheses, open parentheses n minus 2, close parentheses, open parentheses n minus 3, close parentheses. All of that over 24 times 3. Goodness gracious. It's just seating. It's just so, okay. All right, so, and this is equal to n times n, open parentheses n minus 1, close parentheses, open parentheses, n minus 2, close parentheses, open parentheses, n minus 3, all of that over 8, right? So, whoops, yeah, but you get what I mean. So, for n greater than or equal to 4, there are n times open parentheses, n minus 1, close parentheses, open parentheses, n minus 2, close parentheses, open parentheses, n minus 3, close parentheses, all over 8 permutations in S sub n that are products of two disjoint 2 cycles, right? So that's pretty good. Now let's move on to exercise 18. Let's see. Okay, clear the board. Clear the board. Could be another way, you know. I don't know. Okay. Oh, right. I said I would replace this because it's getting out of it's running out of ink. Yeah. So let's I've got this default one. I have other expo ones, but I want to use the default one. So with this default one, I will continue the proofs. So let's see here. Exercise 18. Find all numbers. Find all numbers. That's it. Find all numbers, right? And you go negative infinity union with infinity. Find all numbers and it's such a terrible thing. Such that, no, that's not the worst. It's just kind of silly. Such that S sub 5 contains element of order n. I really hope this erases as good as the expo markers. You only have 5 seats to move. That's the sort of thing here, right? Every permutation of the set containing 1, 2, 3, 4, 5 breaks into disjoint cycles whose links add to 5. The order of the permutation is the least common multiple, the LCM, of those cycle links. So the goal here is to list all partitions of 5, take the LCMs, and collect the resulting orders, right? So let's go ahead and show that. So by exercise 15, we have that if sigma is within the symmetric groups if the symmetric group S sub 5 has disjoint cycle links, sorry. M sub 1 all the way up to M sub R, then the order of sigma is equal to the LCM of M sub 1 all the way up to M sub R. Now, all possible disjoint cycle types are the partitions of 5. So we've got 5, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 1, 2 plus 2 plus 1. Gosh dang it. There's got to be a workaround for that. But, okay, so 2 plus 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1. Now, taking least common multiples of the parts gives the set of possible orders such that we have, this is going to take up a lot of space, so I'll probably have to erase the entire board. Yes. Okay. All right, that erase is pretty good. Usually the default, well, I don't know about usually, because I do not have a statistically relevant, big enough sample size to say one way or another. But for me, what I've generally found is that using the default crappy marker usually just kind of, it's harder to erase than Expo markers. So some people might have very different experiences though. So, but the cycle type, so we've got the cycle type over there. We've got the order over here, and we're having a good time. So cycle type, open parentheses, 5, close parentheses, order 5, cycle type, open parentheses, 4, close parentheses, open parentheses, 1, close parentheses. That has order 4. Now, how about this? Open parentheses 3, close parentheses, open parentheses 2, close parentheses. Well, we know that one. We've seen that before a whole bunch of times, and that one is equal to 6, right? So, how about this? How about the disjoint cycles 3, 1, 1? And at this point, I don't really have to say the parentheses too much anymore, because I can just say disjoint cycles, for instance, 2, 2, 1. See that? And what's the LCM of that? Well, that is 2. Okay, now how about 2, 1, 1, 1? Well, that's going to be 2, right? So now how about this? How about 1, 1, 1, 1, 1? Well, that has order 1. You know, you so fast you could say it by way before I finish saying it. So thus the possible orders in S sub 5 are precisely the set containing 1, 2, 3, 4, 5, 6. So S5 contains elements of order n exactly for n within this set. So that's it for that. Now let's move on to this other exercise, exercise 19. Okay, well, for exercise 19, we've got this, which is find Waldo, find all numbers. Again, you have to find each and every single last number, each and every single last one, and don't even try. Just stand there face to face with me if you haven't found each and every single last number. Don't even try. Okay, it's just pathetic. No, but find all numbers n such that S sub 7 contains an element of order n. Of order n. Doing that Khan Academy thing. I mean, this whole thing is kind of a Khan Academy thing. He was the first one to really sort of do this stuff, but like, yeah, every once in a while I catch myself doing it, but there's nothing wrong with that. So every permutation of the set containing 1 on and on and on to 7, well, that breaks into disjoint cycles whose lengths add to 7. And by exercise 15, the order is the LCM of those cycle lengths. So list the partitions of 7, right? So take LCMs and collect the distinct values. So what would that look like, right? So all disjoint cycle types correspond to partitions of 7. So for instance, 7, 6 plus 1, 5 plus 2, like before. 5 plus 1 plus 1, 4 plus 3, that's fine. 4 plus 2 plus 1, and then 4 plus 1 plus 1 plus 1. Then we have 3 plus 3 plus 1, 3 plus 2 plus 2. And you could do this, you know, until we reach the very last one, which of course would be 1 plus 1 plus, that's supposed to be 1, 1 plus 1 plus 1 plus 1 plus 1, right? 3, 4, 7 ones. So taking least common multiples of the non-trivial parts come on, gives the cycle type. That's going to take up the entire board again, so let me just check the camera real quick. Because if I would have checked it, I feel like I would. You see, this is what happens when I don't check the cameras, right? In the last video, the rotation was off. Hopefully I can fix that in post. It's a George Lucas thing, but I'm taking it. It's fine now. No, everybody fixes things in post. Well, no, that's not true. But let's just erase this. Clean slate, wipe the board clean. It's a pretty dark prospect when it comes to humanity. Just wipe the board clean. No, but sounds like something that would be said by AI or whatever. No, not whatever, but just by AI or aliens, you know, future stuff. Cycle type. So that's just the cycle containing only 7. So the order of that is, of course, 7. Okay, so disjoint cycles 6 and 1. What's the LCM? It's 6, right? So then we can just continue this process, right? Disjoint cycles 5, 2. 5, 1, 1. Come on. There we go. So orders of that would be 10 and 5. And we continue along this path. Right, so and we get 12, oh, sorry. I should just write it without really saying much. So, how's the weather today? Make small talk while I'm writing these, I guess. Oh, it's pretty good. Did you hear that Sheila doesn't like Tommy anymore? She was killed by a bloody wallaby. It's a horrible way to die. That's why in Australia we have such silly names. Keeps our humor up. No, I'm not in Australia, I'm in Oklahoma, but all right. is exactly the kind of thing I wanted to avoid. No, but you see here we have the 3's, right? The ones that start with 3, and here we'll have the ones that start with 2. Gosh dang it, come on. Wait a minute. That's not supposed to be there. Okay, and then finally, let me just kind of mark that out and say 2, 2. And then 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Then we have the 7 disjoint cycles of 1, order 1, right? So, ergo, henceforth, to be or not to be, that is the question. No, wait a second, that's not right. No, but hence, the possible orders in S sub 7 are exactly say it with me now. 1, 2, 3, 4, 5, 6, 7. Wait a second. Wait just a minute. Interesting, right? So we've got to be careful. Got 10, 12. So it's the set containing 1, 2, 3, 4, 5, 6, 7, 10, 12. What a weird counting order, right? It's like ABCs and then you skip the middle part and you forget how the song goes. It's a nightmare. All right, on to the final question for section 1.3. Let me check something real quick. Okay. Exercise 20, right? So let me check that. Okay, looking good, looking good. Time-wise, we're looking pretty good too. How about space-wise? Space-wise, we're working on that on the board anyhow. Okay, so let's go to exercise 20. So exercise 20, it says, well, hi there, I'm exercise 20. No, it doesn't. It can't talk. It's an exercise. Stupid. No, but find a set of generators and relations. Don't forget the relations, right? Present, and I don't know. For S sub 3. Find a set of generators and relations for set sub 3. It didn't say that it has to be a correct set. No, that's stupid. Okay. Intuition. S sub 3 is the group of all symmetries of a triangle. 2 moves obviously generate all symmetries. I mean, a flip alpha across an axis, a transposition, order 2, and a rotation beta by 120 degrees, so like a 3-cycle order 3. The only extra constraint you need is that flip, then rotate sort of thing, behaves like a half turn. The cycle, open parentheses, alpha, beta, close parentheses, as order 2, those 3 facts pin the group down, right? So, well, you know, I say right often because that's just my kind of, everybody's got like their own, I've said this before, a subconscious vernacular set, right? So, right, and like all of that sort of stuff that makes some people cringe is probably very much within my set. Okay. So let's prove this. So let's see here. D-dum. Let alpha equal open parentheses 1, 2, close parentheses, and beta. I had a professor that called it beta. I was like, oh my gosh, that sounds so fun, but I can't do it, I'm sorry. Alpha is equal to the cycle open parentheses 1, 2, close parentheses, and beta, which is equal to open parentheses 1, 2, 3, close parentheses, in S sub 3. Then alpha squared is equal to 1, beta cubed is equal to 1, and open parentheses alpha beta close parentheses squared is equal to 1. So we claim, me and the collective board of scientists, no, we claim, so that's just, a neutral sort of thing, that the presentation, though I feel like saying I claim would be, but that's not, I don't know if I like that, like why we say we instead of like I get it, it's kind of like a neutral thing, but it's also like, it's kind of cowardly in a way. How do I say this? It's very, a man should stand behind his work sort of thing, but anyhow, we claim that the presentation alpha beta, such that we have the relation, so these are the generators, alpha and beta are the generators, and alpha squared is equal to beta cubed, which is equal to, if it did something weird there, we'd have a dihedral group on our hand, right? So remember that. So open parentheses alpha beta close parentheses squared is equal to 1. That's our relation. And that defines S sub 3. Good. Now, so we've got, so let's see here. So we're told to just find a set of generators and relations for S sub 3. Okay. So that's our claim, but we've got to prove it. Got to prove it. So step 1. I mean, it doesn't say to prove it, but I feel like we should. So we have alpha beta. This generates S sub 3. That's what we're saying. Now, since alpha is a transposition, and beta is a 3-cycle. Anytime I see like 3-cycle, 4-cycle, 2-cycle, I just think of motorcycle engines. Not just, but I do think of motorcycle engines. Since alpha is a transposition and beta is a 3-cycle, they generate all of S sub 3. Indeed, open parentheses 1, 3, do I need that? Yeah, is equal to beta alpha, and open parentheses 2, 3 is equal to alpha beta. So, okay, let's see. Since alpha is a transposition and because they generate all of, so they don't commute though. It looks like they don't commute, right? No, wait, these are different generators. Okay, so all 3 transpositions, no cispositions, just transpositions, and the 3 cycles, well, those lie in the group generated by alpha beta. So the group generated by alpha beta is equal to S sub 3. Good. Now let's move on to step 2. Okay. This mosquito bit my leg, and it is... Why don't we just get rid of mosquitoes, man? I know there's like some environmental factors and like whatever, but like, you know, just do it. Just one time, just for one time, purposefully do it. Now, I'm sure it's not the first time humanity has purposefully driven something to extinction, right? Has to have been something else. Who knows? Well, no, there's got to be somebody who knows. But, step 2. The relations hold in S3. That's what we want. We want the relations to hold in S sub 3. Direct computation. Direct computation gives alpha squared is equal to 1 and beta cubed is equal to 1. Also, alpha beta is equal to open parentheses 1, 2, close parentheses, open parentheses 1, 2, 3, close parentheses, which is equal to open parentheses 2, 3, close parentheses. So alpha beta, so open parentheses alpha beta, close parentheses squared is equal to open parentheses 2, 3 squared, which is equal to 1. Therefore, there is a surjective homomorphism. Phi is equal to G group, which is generated by alpha beta, such that we have a relation alpha squared is equal to beta cubed, which is equal to open parentheses alpha beta squared, which is equal to 1. And this is equal to, well, no, it sends generators to the indicated permutation, so therefore it is equal. So so sending the generators to the indicated permutations. Now, let's go on to step 3. So for step 3, normal forms in G, size less than or equal to 6, from open parentheses alpha beta close parentheses squared is equal to 1, we get alpha, beta, alpha is equal to beta to the negative 1, in which we multiply on the right by beta alpha. Hence, alpha beta is equal to beta to the negative 1 times alpha, and beta alpha is equal to alpha beta to the negative 1. So that's why we weren't, yeah, those two things aren't the same. So using these, any word in alpha beta can be rewritten by pushing every alpha to the left. So it's a Marxist now, but no. Reducing powers with alpha squared is equal to 1, and beta cubed is equal to 1 to one of the 6 forms. It's one of the 6 forms, which are 1 beta, beta squared, alpha, alpha beta, alpha beta squared, which, you know, should remind you of something, right? Definitely of those tau sigma things. Those tau sigma. Whenever we looked at those, whenever we looked at the sigma tau cycles and like all the different ways we could manipulate that. So that's neat. Let's go to next page for my notes, which is, well, to state first of all, therefore, the order of G is in fact less than or equal to 6, right? So we have that in hand. So what else can we say? Well, for step 4, we discussed the notion of being an isomorphism, which I don't know, how does that, it's strange, because isomorphism, the notion of an isomorphism, but if it's isomorphism, I mean, then again, it didn't ask for a proof, right? It just told us to find them, right? It asked us to just find a set, and not even a correct one, but okay, but okay, no, you shouldn't have to say find a correct one, because if it's either in the set or it's not. So now, so step 4, which isomorphism hasn't even been discussed at this point in the book. So I'd be surprised if they expected you to prove all of this, right? So, but the images under phi of the 6 normal forms, which kind of reminds me of like standard basis vectors and all that, but my memory's too old on that. So the images under phi of the 6 normal forms are the 6 distinct elements, these being 1 and open parentheses 1, 2, 3, close parentheses, open parentheses, and also, I should say, and also, so that way there's something representing a comma there in my sentence, but open parentheses 1, 2, close parentheses, comma, open parentheses, 2, 3, close parentheses, comma, open parentheses, 1, 3, close parentheses, of S sub 3. So we have the identity and the following disjoint cycles: 1, 2, 3, 1, 2, 2, 3, 1, 3, and these are all of S3. These are all of S3. Oh, no, these are of S3. 6 distinct elements of S3. These, yeah, well, sometimes I correct myself when I don't have to. Hence, phi is a bijection. There's a more precise way of doing that. And group G, which we were describing, is isomorphic to S sub 3, which is like sort of roughly equal sort of thing at this point. But a presentation, which is the, what is that? It's not exactly a set, is it? I mean, it's kind of a set. It's the group generated by these generators, S sub 3, it's roughly to the group generated by the generators alpha and B, such that we have the relation alpha squared is equal to beta cubed, which is equal to open parentheses alpha beta squared, which is equal to 1. And this is with alpha equal to open parentheses 1, 2, close parentheses, and beta equal to open parentheses 1, 2, 3, close parentheses. And that is it for section 1.3, and we haven't quite hit the hour mark, but that's fine. We just finished the exercises for 1.3 symmetric groups, so we are good. That is all for now.